Hello, everyone. This is Harsh, Program Manager for CFD Modeling Solution. And today we'll go through another quarterly release update, which is HyperWorks CFD 2022.2. Too many twos in that. So I'll first cover the modeling updates, and then later Mike will cover the post updates, and then we'll go through the future roadmap aspect. So for the modeling updates, we have three items. One is we added the AccuTrace support. Then next will arrow modeling process and design exploration capabilities. This release, we focused on the customer requested solutions and added those support in our UI. So let's get started with the AccuTrace support. So we added the capability where you can set up the particle tracing utilizing the AccuTrace. It is a seamless extension to our AccuSolve support. So the user can support their flow model. And then once the solution is done, they can set up their AccuTrace. It is requested by 20 plus customers, specifically from Japan region. And there are already a couple of other customers lined up, which are not already using this. So setup is pretty straightforward. So let me go through that. We open. So this is a simple example which is added to the tutorial. The geometry is validated. The flow setup is done, and we already ran the simulation for the flow in this static mixture. So here we are adding two species, one and it will be mixture. It will be mixed. We are simulating the mixing throughout this channel. So once the flow setup is done, you can go through the AccuTrace. So this is the entire ribbon where you can set up the AccuTrace. So in the setup panel, you can set up whether this is the finite mass or massless particles. Point to the directory where you have the solution for it. So here I'll point it to the AccuSim directory where I have my flow solution. So it will populate like what is the run ID from which you want to extract those data. The name of this will be automatically grabbed from there. And if you want to update, so this is finite mass. So if you want to update any of the material properties, you can add it here. Next, we can define the seeds. So there are two ways. If you have the model, you can interactively define the seeds on this inlet. Another option we have is to bring up any seed data. So here I'm bringing all the seed data. You can set up your parameters, which is basically the emission time, the time interval. So here I can say find those and interval. And then I'll also bring in the seeds from the other inlets as well. So you can open that CSV2. This, if you don't have the seeds input, you can also extract the seeds from the post-processing post ribbon as well. So once you define solve, we'll go to the same emission stopping and the time interval. Once it is done, we'll go through the setup of the what are the reflecting walls. So as soon as you click on the reflecting walls, it will show up that what are the available boundaries in your simulation. So you want to define the pipe wall as the reflecting wall, and we can define the restitution vectors. And the second, we want to define the fin walls, which are the inside mixture wall as those walls. So we can define those parameters. So once this is done, and then we'll define the stopping walls. So outlet is our stopping. So we'll find the outlet as the stopping. And then once this is defined, you define the output, that how many output frequency you want, and you can run the AccuTrace from here. So you can define your AccuTrace trace path and click on run. So once this is done, you run it, you convert your AccuTrace data to the convert tool, and then you can post process utility. So it's a pretty straightforward workflow, and it is completely integrated. So you can run your AccuSolve simulations, and then once that is finished, you can go for the AccuTrace simulation. Another another solution which we added is the capability for external error modeling. So this solution we have added through extension. Extension is a capability in HyperWorks CFD where we can define custom tools for specific workflows. So for external error, we have added this extension which can cover start to end modeling workflow in a single ribbon. The input data can be CAD data or the discrete data or even scan data. We have many automated tools, and I'll go through some of the tools and provide you demo. And this process significantly reduced the modeling time. This is being developed for one of the benchmark in the Japan team, and it is already deployed at their site, and they're currently utilizing that. For their benchmark, we got the CAD data with around 11,000 parts, and it took us 34 hours to prepare the model for UFX. It was the full, excuse me, it was the full vehicle model, and you can see all the details there. And this is the time data which is providing the time, and most of the time, so around 34 hours, 12 hours are just a computer time, ranging from imports or the wrapping time or some of the operation time. So this is a significant solution which is generic, so it can be deployed to any other OEMs as well. Let me provide you a demo of simple assembly. So I already loaded the extension. So you see that I have the ribbon called external error modeling. And here in this ribbon, I have all the tool sets which are required to prepare the model. So for this demo, I'll just go through a single suspension assembly, but the same thing can be utilized for other things. So let me copy path. So first is the part browser. So you can invoke the part browser. Import. So import allows one of the feature which we have is the bulk import. So if you have multiple CAD file or STL file, you can point to the path, define the extension for that path, and you can, based on your requirement, you can either choose to remove small bodies, split parts, or anything. For this one, we don't need that, and we can just click on bulk import. So that will go ahead and bring in all the files with the extensions of STL within the model. So this is a public model, but it is quite detailed. So it has around 325 odd parts, and for this process, we'll go through the tools to show you the process. So one of the tool in this extension is the find tool. So here you can select the parts, and you have the options to either find the duplicate parts or tiny parts. So here I'm just choosing that find me the tiny part and click on the find. So it will go ahead, scan through all the parts, and it will find you all the tiny parts. And it will create a group out of that. So we can choose those tiny parts. So isolate them, so it will find all those tiny parts. It is not for UFX. It's not needed to remove those parts, but it's an option for us. So once this is done, there are tools to if you bring in the CAD data, there are tools to bulk mesh those parts or convert those CAD models to the discrete models. Another challenge is many times we have coming the parts as the baffles or bed surface. So here you see this example that this part is baffle. So we have this option where we have some tools to find those and inflate those. So you can see that I can click on find baffles. So that will go ahead and based on the ray tracing, it will identify the parts which will or the elements which can be acted as baffle. It just found few elements of those parts because those are the only the other parts will be connected during the wrapping process. So I can select these parts and so I can select this part and probably let's go and inflate them. So I can say isolate only and go to the tool again. And I select both the parts, define the thickness, and I can do thicken shells. So it will go ahead and add the thickness to those parts. This step is automated into the wrapping process as well, so it's still optional. Now, once this is done, you can go through the hole fill. So if you have pipes and those type of structures or fill out any bolt holes, so you can just select all the parts. There are options where you can define what is the maximum threshold which you want to fill, remesh and all those things, and then you can patch all the holes. What it does is that it identifies all the feature loopholes and fill it up. And since we turned on the remesh options, it will also remesh based on the neighboring size. So you can see that all those holes are filled. So then we can, there are several other tools if you want to trim and all those things. We don't need that. So we can just go through the wrapping process. So here we can select all the parts. And these are some of the wrapping parameters. So we'll just change some of the parameters. We don't need the leak check for this, and we can enable the quality and define the maximum allowed gap because this is the suspension, so we don't have a major gap on this one. So we are defining just S4. And once you define those parameters and click on the CAD wrap. So while it is running through this process, let me explain what this CAD wrap is. So in traditional modeling approach, the powertrain or underbody parts are wrapped using the traditional wrapper, and the upper body parts are stitched and connected together because the traditional wrapper does not preserve the features, the upper body features precisely. Whereas this CAD wrap, it's different from the traditional wrap. It keeps all the parts which are not touching or anything else as it is. It will only modify where the connections are needed. Some issues into the mesh needs to be fixed. So that's why it is called CAD wrap, because it keeps all the geometry, the discrete geometry as it is. Another thing is that it extracts the faces pretty nicely, such that you always get a watertight tight model without any issues. So this is another approach which we have added a couple of releases ago. And in the last release, in the .2 release, the performance is improved significantly. We multi-threaded this CAD wrap. So for the cabin model, it takes around 30 minutes. Which is pretty good timing considering like the number of parts which cabin has, and specifically the features it preserves. So it significantly improves the feature capability. So it reduces the time, the manual time which are needed to trim or patch the gaps into the. So this will take around 2 to 3 minutes. Yeah, another advantage for this wrapper is that for traditional wrapper, you need to know the sizes. Like what are the sizes you need to apply on different domains. So the know-how of like how the wrapper works and coming up with the best practices is more trickier, and you have to run through different iterations to come up with that best practice. Whereas in this one, user does not need to specify any sizes at all. It will by default preserve all the gaps and features as it is, which is required for the external aero modeling. So now it is going through the auto cleanup. So the auto cleanup part will try to fix all the issues, remaining issues from the wrapper, and then at the end of the wrapping, yeah, it will give you the results. So you can see that it wrapped everything. All the connections are made. So you can see all the bolts and everything are now conformally connected. All the parts are conformally connected, and you can see all the gaps and everything is preserved, and all the shape, it did not. All the shapes is preserved as well. So this is pretty significant utility. And this is just a one assembly, but if you bring in the entire powertrain, you can run the wrapping on that entire powertrain as well. Another set of tools which we added, some of the mesh update tools, quality, and the normals as well. So one of the requirement for the external aero case is has to have the normal consistent. And the wrapper, when we do it, it will make it most of the part consistent, but some of the elements can have. So if you want to fix that, we have this utility to automatically fix those normals. We have two approaches. One is using the ray tracing, which shoots the rays and identify what are the exposed elements and fix the normals. And another is based on the connectivity, where it can fix the normals based on the connectivity. If anything is not fixed, you can select this, and you can update it based on the connectivity. So now it will update the normals based on those, and you have consistent normal. Mesh updates also has some nice tools like the decimation part of it, that if you want to reduce some of the element count of it, so you can just select this parts. I'm zooming it so we can see. Define like I want to decimate anything less than 25, and feature angle, which will say that, okay, how much geometry I can modify. So to degree, it will not modify much. So any flat plates, it will go ahead and remove the nodes to make it to reduce the. You can see that it significantly reduced the elements to the top side. So yeah, this is the process, and then we also have the bulk operations. So if you want to run all these tools in sequence as well, then we have this bulk operation tool where you can go through all these tools automatically in sequence. So this is about the external aero workflow. And we also have so enclosed region creation. So if you want to create some refinement regions around the cabin, then it can define that. So entire from starting from CAD to the final mesh workflow is within this ribbon. So this is very customized solution for external aero modeling, and it's pretty generic, so it can be utilized for any customer, and it's public. Next solution which we are asked is to provide the capability to do the DOE studies based on the morph shapes, and we added this also part of extensions. This extension will provide you to perform the DOE studies based on the morph shapes, meshing parameters, and as the setup parameters. It is integrated with the existing AccuSolve setup process, and we have added the interactive tools to create the morph volumes and create the shapes. And this can be utilized for UFX as well, to perform the morphing and run the DOE studies. And once and it also pass the data to HyperStudy, so you can perform all the studies in HyperStudy. So let me go through that. So as I have external aero modeling, I have another extension. So I can go to Extension Manager, add extension, and I have the DOE extension. So if I enable that, it will add the ribbon called DOE. So this has all the tools for defining the morphing. So let me open the model which I already prepared. So let me first start with. So this is the model where geometry is validated. We set up all the flow and meshing parameters, and we perform the surface meshing already onto the geometry. And then we define all the surface monitors which we want to utilize as the response surfaces. Once this is done, next tasks are simple, that you can just go through the DOE ribbon and define the morph volumes and create the shape. So quickly, I can just go through how you can create. So you can just select few nodes, and you can see whether you want to define globally or best fit. And then you can split the morph volumes to add more control points within devs, and you can enclose that. There are several tools. So you have tools to even split further. So I can say I want to add 2 more splitting points. So you can add more control points as well. And also you can reposition this control points to closer to the geometry. So you can select that and you can reposition it such that it can be closer to the geometry. So you have more controls when you are morphing your shape. And regarding the morphing, you can also morph the shape by moving the nodes, individual nodes, or you can by any edge or any face. So in this case, you can just pick a face. Okay, so once this morphing is done, you can add this as shape, and you can review those shape. Just to quickly show you, I already created the shapes on both sides, so you can have it on both sides and already define the design variables based on this shapes. So left elbow and right elbow. The only thing I need to do is click on this HyperStudy launcher. It will populate all the fields by default, and I can define I want to use 6 processors for the solver run and meshing run. And also it has the options to do the shape studies or the solver parameter based studies or mesh parameter based studies. Solver can be AccuSol and UFX, and based on that, it will export the relevant files, and we can point it to the relevant solver directory. So here I can select the AccuSol file, CFD solver, AccuSol, the bin directory, and say OK. And then I'll define that I want to observe mass flux on all my the surface outputs which I have defined. So I can select n number of outlets, and then at the end of the run, if I want to write out the results as any of the file, I can define that, and you can just click on launch. So this will go ahead and put all those the setup. It will write out all the scripts required for this simulations, and it will have this by default setup. And you can say import variable, and you can see that whatever the variable you define in your UI will be brought in, and then you can start writing and executing this process. So this will start running the AccuSol, and based on this, you can perform the DOE studies. So it's pretty neat feature, and this can be utilized for doing the shape-based studies, mesh sensitivity studies, or the setup parameter-based studies. So those are the three major features. So HyperWorks CFD has created the tools to have a lot of applications, and let me just go through some of them. So for automotive side, for this release, with the extension, we'll be able to go through the external aero modeling, cabin modeling. We already have the setup for that and the tutorial for that, and so for the battery cooling and the underhood cooling. So We are still working on adding and improving those, but right now we have a solution where you can perform all these applications with HyperWorks CFD. For next release, targets for the modeling, they'll be working on the discrete modeling workflow, light modeling, so that you can bring in CAD data quickly and review them. We are also started working on integrating HyperWorks CFD and VWD, so we can seamlessly exchange the data and transition to the UIs. On the wrapper side, we are working on the auto seal capabilities and some of the auto refinement zones or MRF region creations. And yeah, units is coming along for the next release as well. And some of the improvements on the geometry side and the wrapper side and the automation side is also targeted for next release. So a lot of features are already there, and many new features are coming up to make the tools more competitive. So with that, let me hand over to Mike for the post updates.
All right, thanks, Harsh. Thanks everyone for joining today. So I'm going to pull up my presentation here. So this presentation is sort of an accumulation of information that I just wanted to put forth and let the whole community know, as well as new features that came along with the 0.2 release. So just going into the outline here, first I'm just going to review our feature map and the enhancements that we plan on adding for 0.2, give an overview of that, including a summary of the defects. And then I wanted to just give a basic outline of what the UI looks like and some of the tools that are present, but maybe not everyone utilizes or sees. So I was able to go through some of those. I'll go through each of the visualization entities and give some details on them just to kind of set the stage for what is coming in 0.2. And that will be the remainder of the presentation there, is just to review what came out in version 0.2. So using Jira, I was able to create this sort of histogram of terms that we call out in one of the attributes CFD feature. So in the last release, we did focus a fair amount on things like post-particle tracing, streamlines, engineering quantities, and all these requests came in as individual requests perhaps, or requests from different customers. So we tried to listen to the field, as well as taking content information from everything that's been accumulated over the years, and come up with a list of features that we think can deliver. So for 0.2, we know we needed some more information and a feature to kind of cover what engineers typically rely on when they make their CFD simulations. So we've added engineering calculator, which I will go through each of these individually. So in addition to that, we also now have the capability to do intersection curves for 2D plotting. We enhanced the scalar and added box clipping, so we can actually clip by region, not just a scalar. We added the ability to bring in XYZ and coordinate variables. And as Harsh reviewed, we do have now the particle trace support via AccuTrace. And then we also made some minor modifications to read in that data in NSIDE format so users can view that. So just a little bit more details on each of the different sections. So those are essentially the RFEs. We had 7 major ones that kind of summarized down to those ones I just mentioned. There were a number of defects listed and fixed for 0.2. So we had a total of 30 tickets. For the most part, we kind of covered those 30 tickets across these 5 individual topics. So adding the ability to automatically scale based on a given entity is now done across all of the entity types. So we just modified a couple of the behaviors there. We've added multiple selection capabilities. So for the most part, now users can use the post browser to edit and manipulate multiple entries within it in the same way that they could modify a single entry before. As far as the reader options, we have added the ability to turn on and off extended variables coming from AccuSolve. So this is helpful for users who may need to have some of the extended nodal output, but they don't necessarily need all of, say, the gradients or some of the residual information. We've added the ability to do streamline animations, which is helpful for basically cutting a video from a steady state time step. And then we also fixed some of the issues with saved views. So there are a few more improvements that I'll try and touch on in the rest of the presentation here, but this list is really just for archive purposes. So I just wanted to kind of set the stage. I don't have a demo today, so just running through these slides. Here's what the post browser essentially encompasses. So just wanted to point out first that we do have a unique help for post. So all the entries within that help manual are set up for post processing. We'll be adding to that in future releases. For now, basically, there's just a small blurb about each of the individual entities and all the different tools. But as you guys are probably familiar, we have a number of different entry points to interact with the model. So the post browser is often used to really show and hide items. That's typically how I use it, but it's also integrates a lot of the HyperWorks usability. So we have things like find and search to manipulate that post browser. And then we can also utilize the active and inactive dataset state. So in some cases, you may need to import more than one model. And in that case, you can activate that single model and then work on that model all through the post browser. So you see we have the visualize tool set, which is kind of your basic or the first entry point for adding a scene item. And then we also have the measures tool set, which is a little bit more on the quantifiable side, where we're actually able to, say, probe or integrate the data set. We can also compute derived values with the calculate tool. And then also, as I mentioned, the plots and the engineering quantities tool. We also added the notes tool, which has been around for a while now, but it is helpful to annotate a model, and there are a couple variable accessible variables within that notes annotation tool that can plot, say, the time step or the model information. And then just kind of a duplicate slide to also just point out that between the post browser, the advanced search and select tool, as well as the grouping tool, we do have a ton of capabilities that aren't immediately present to the user, but that do actually reduce the click-through times and the overall time needed to post-process a model. All right, so I just wanted to point out one of those here. So this is one of our internal external arrow models. And this model had a ton of different parts in it that came through VWT. And one thing I noticed right away is that there are baffles within this model, right? There's duplicate surfaces right near the hood region where the solver is able to compute the flow on the external and the internal side of that hood. But in order to do that, it needs two sides of that wall. So when this model came in, it has those surfaces tagged individually with this INV text string added to each of those groups. So if we go ahead and use the advanced search tool to search for that string and then select all the items that contain that string, I can do an inverse selection here and then basically select the rest of them. And I wanted to do this just essentially to isolate those parts and remove that baffle from my view. So that's what I do here. I go ahead and just isolate all of those parts. And now instead of having that duplicate baffle within the scene, I just have my single normal direction parts viewable here. So here I'm using the auto calculate, which goes and finds the min-max of those selected parts. And you can see it does take a minute to update here. This is a pretty massive data set. But once that's done, I can exit the tool, and essentially we get our pressure contour on the surface of only the surface we're interested in. So I think I was pretty in awe at some of the resolution in this model. So this is one of the first times I was going through it. It's pretty impressive, the number of parts and the information that one can obtain from an ultrafluidic simulation. As many of you know, I've been in the AccuSolve world for so long. A lot of times we'll just smear out some of those parts. But with ultrafluidics, of course, we're able to get that extra information about the model that we haven't been able to in the past. All right, so drop in next. So one thing we have that isn't immediately available in the front end because it's behind a right-click option is the apply state. So if a user goes and saves off a state file, which is essentially an entry point to the visualization scene that they've created, they can apply that state file to subsequent data sets. So here I was just making an example of two turbulence models used in AccuSolve. Flow moving across this train model. So in one case, I had the SA model simulation run, and I did some basic streamline processing. And then I wanted to see, okay, if I use those exact same seeding points and surface streamline contours, where does the flow, what are the differences in the flow when I'm using SST? So you can see that there are some minor differences in the solution here, but for the most part, they are very identifiable as the same solution, pretty close anyways. So this is really nice when you need to repeatedly check the same quantities and you have different flow conditions that you need to review. All right, so next, basically running through all the individual visualization features that we support. So this is nothing new necessarily, but I just wanted to kind of set the context for the new features for point 2. So boundary groups is, of course, typically the first thing that you see when you open the model. We can actually color the model by default, given a user preference. So in this case, I do have a derived value here, and that's temperature in Celsius. So I computed this using the calculate tool just to subtract out the 273.15 to go from Kelvin to Celsius. So I have access to that variable on the boundary groups once I've predefined that. And yeah, here we're just demonstrating, okay, we can have a boundary group and color it by temperature in that derived contour. So I tried to make an example out of slice planes to show that, okay, yes, you have your basic slice plane, but there's also these individual display properties that we can add to kind of enhance that item or highlight certain features of that slice plane. So first off, we just have a slice plane showing here the instantaneous velocity in the wake of that vehicle. But if I wanted to add additional information, I can go and not only change the slice plane properties, including the legend and the warping of that velocity function or that velocity surface. I can also look at the vectors or contour lines, and I can plot the grid or the contours of the mesh. And then I can also plot the outlines, which is helpful for the ultrafluidic simulations where you have different refinement levels. The contours, the outlines show those contours of that mesh. So here's what each of those individual items looks like. So we already saw the slice plane, but we can also plot contour lines with a user-specified number of intervals between those contours. We can also plot vectors in that slice plane, and these can be projected vectors. And so we can remove one of the components of velocity if the user would like that, or we can actually use the tangential to see the in and out of plane vector if you're interested in what your crossflow behavior was. As I mentioned, we can also look at the grid and the outlines. So you can see here the outlines do indicate the refinement levels of the ultrafluidics simulation. So it's just a small indicator on where those changes in grid occur without having to plot all the dense cells like we show in the grid display. Yep, so just the last two. So I just wanted to make note of the warp function. So this is embedded in the first visualization piece for slice. So if the user likes, they can actually add a bit of in-plane warping. So actually, it's out-of-plane warping, right? So it's actually pushing that function in and out of the plane on the screen. So a user can select their vector and then some magnitude to actually warp those cells by. So I kind of like that. It does help to really kind of enhance high gradient features. So you can see the shear layer under the vehicle body here, where it is warped. There's a pretty clear, distinct demarcation mark there. We can also add transparency. So if the user needs to, they can add transparency all the way up to fully transparent, like I'm showing here with vectors plotted as well. So as far as ISO surface, I don't have a ton of content here, but just to note on that same model, we can plot, say, ISO function of x velocity of 0. So the instantaneous time where the flow is recirculating is shown in these plots. And of course, we can look from the different view angles that were saved into the into the scene. And then lastly, just quickly on streamlines, of course, you can add multiple visualization types and kind of get the scene where you see, okay, I see my recirculation zone, but I can also see my shear layer and the corresponding velocity for all of the points, in this case, that were seated within that ISO surface. So just one other thing to kind of highlight here is that, yeah, we can now seed from derived entities. So under the Streamline tool and Surface, I can now select a slice plane. So in the past, we didn't have this entry point, but now you can essentially create a slice plane that is unique and outside of the other entry points. So that slice plane maybe have already been pre-selected. Now I can just go in and select that slice plane and automatically seed it and then create the streamlines from that. Similarly, another way to create streamlines, in this context, I computed the vortex core, and you can see the vortice cores here with these gray lines. And in this case, I actually used Rake to create a few points along that vortex core. And they do coincide with the vortex core mostly, but they're not on the vortex core. They're just kind of in the region. And I was able to just use the vortex core to eyeball essentially where that rake started and ended. But once you do that, you're able to compute those streamlines, and we can see that we really highlight the vortex core and the big amount of rotation that's in this flow in particular. In point 3, we are working on directly seeding those vortex cores. It's already available in an internal build, so just wanted to kind of explain the differences there. Here we're using Rake. In the future, we'll have the ability to seed a vortex core directly. So Harsh already covered, for the most part, AccuTrace particle support. I just wanted to put this here because it is a post operation as well. So for this model, we're able to do a finite mass particle trace on a multi-phase flow where we introduce particles at the inlet according to a streamline set derived from post-processing. So we actually just import those seed locations here, and they were able to run the finite mass particle trace and essentially watch these weighted particles get sloshed around in the liquid phase, and then some of them exit the domain. So one more example here of finite mass particle tracing. In this case, we have a time-dependent inflow and then also a inlet-dependent weight on the particles. So one side of particles that are injected are slightly heavier than the other. And then, of course, we have this time-varying inflow. So we actually see that the particles get suspended within the tube here and then are pushed again outward once the flow speed ramps up. So we can also plot other information on those particles. And so one of the nice things in Post that we have not had in other tools is the ability to plot the vectors on those seed points. So in this case, we have AccuTrace data set along with an AccuSolve solution where we have a multi-phase flow rotating within this tank. We pick up particles from the bottom of the tank due to, I guess, the rotation of the fluid velocity here. And then we can color those particles by velocity magnitude and then also add the vector scaling based on magnitude. So I kind of like this simulation and the result that we're able to review here because it does give you an indication of where you have those high rotations in the flow. And then I think it does highlight pretty nicely how the particles actually move within this flow field as opposed to just showing the particles alone. Okay, so moving on to the next new feature, which is scalar clipping. So we now have the ability to clip a representation by a scalar. So you can utilize boundary groups or slice planes, ISO functions, and then clip those derived representations based on a scalar function. So in this case, we're showing a granular flow example where we have the boundary group of all the surfaces within the model that is clipped by the volume fraction of copper. So you see in my animation here on the right that there's a small line indicating the free surface of the copper. And then you can see that free surface sort of speed up as it exits through the domain here, and then eventually becomes all liquid and no more solid. So this is a somewhat new feature in terms of its usability. It's been around for at least one release now, but we have just made sure that it functions correctly, and then it's also available now on these derived entities instead of purely boundary groups. We also added a new feature for clipping, which is called box clipping. So basic premise here is that you're able to clip any boundary group or derived group based on a cube. So the user can essentially select the center point and then the length, width, and height of that cube, as well as the entities they want to clip. And that clipping can be assigned so that you're retaining either the inside of that cube or the outside of that cube. So I have two examples here just showing an AccuSolve data set, again, this train model, where my streamlines kind of move pretty far inward and outward within this domain. So if we're interested in kind of just looking at the local flow features here, we can clip that out with a box. So you can see before the clip, I have streamlines moving throughout the entire domain, but after the clip, where I just clip the streamlines and the track, we can just view kind of that one region we're interested in. And there's other ways to do this, but I thought this was an okay way to go about, say, clipping away half the cabin model. So that's what I did in this example on the bottom. We have the interior of a cabin with a human in it, and we can essentially just line up the edge points of that cube so that they hit the midpoint of the vehicle, and then we clip out all of the vehicle content that's sort of into the screen where the viewer is looking from. So I did just want to highlight why essentially we added XYZ coordinate variables. So sometimes users do need to get an indication of the location within their models. So in this case, kind of moving from left to right here, we can look up the XYZ coordinate variables using the derived function calculator. And you can see here we have an internal expression to define those that coordinate vector. So you see we can access XYZ coordinate values, and then I can actually use those in downstream functions to compute. In this case, I just called it the numerator x times x coordinate times time average pressure to compute essentially the numerator in the center of pressure calculation. So you can see in the center block, I plot the cube surface with that numerator, and then integrate that surface to obtain the integral of the numerator and then the integral of the time average pressure on the cube. And if I divide those two out, that computes the center of pressure. So you see, this gives just a single value, and then I can look up via the intersection curve at that location. Okay, what is my pressure across a rake, for instance? And here I can see what's the time average pressure as I move from the recirculating part at the cube, but at the center of pressure. And then similarly, if I wanted to intersect the entire cube and then plot the circumference of that cube or the perimeter of that cube, I can do that on a two-dimensional plot using the intersection curve tool. With the intersection curve, we do have the capability to, like I said, just create a rake or actually plot the intersection. So in this case here, we're just plotting a rake. So it's just a single line of points. And oftentimes users want to kind of tease out a little bit more information about their flow field. So in this case, the user was interested in perhaps looking at the transition model and the results coming from it. And then one of the symptoms of that transition model is the entry of eddy viscosity into the flow field. So both of these plots indicate, with my intermittency moving towards 1, I can see that I do have an increased eddy viscosity at that location. And then that's sort of backed up just by a qualitative contour to show that, okay, yep, there is this shear layer happening right near the foil. And our intermittency goes to 1, indicating that the flow is fully turbulent at those locations. And that, of course, matches up with the eddy viscosity that we plot in the wake of the foil. So, I just wanted to indicate how we could kind of put together all these different pieces. So in this case, say the user needs to compute coefficient of pressure. Well, coefficient of pressure is not in the immediate data set, right? So we need to create a derived quantity to really just non-dimensionalize that pressure field. So in order to do that, I can integrate my far field to compute pressure and then the free stream velocity. I can enter those values into the derived calculator and then create this expression for CP, just P over dynamic pressure. And then I can also inverse that CP because oftentimes engineers, especially if they're looking at foils, maybe not too often, but when we're looking at foils, we want to plot negative pressure. So you can see how we did that in the intersection curve tool here, where we go ahead and cut that surface with a plane and then plot CP on the surface of that foil. So same thing can be done for ultrafluid X data sets. So I just wanted to make sure that that was clear. We can take the exact same steps, and in this case, we did have a little bit of back pressure and of course a different upstream velocity. And then I can use the time average pressure there instead of the instantaneous to compute our time average CP on the center line of the vehicle, which is shown here on the Roadster case. So one new feature we've added is the engineering quantities. So here we have 3 examples. I'm just omitting one because it's kind of a duplicate, but the 3 entry types that we'll present here are the difference for an area average, which allows the user to compute, say, delta pressure from the inlet to the outlet. In this case, it's pretty clear, but in other cases, you might have some slice plane or some other derived entity that you can actually select here in your difference, and the tool will go in and compute the integral on that surface or derived entity, and then do it again for your second selected surface, and then compute the difference between those 2 integrals, right? So that's shown here in the engineering quantities pressure difference. We can also just do standard integrals, so our area average, and in this case, I used a slice plane, and so I was kind of curious, how often does the fluid actually reach the slice plane in this multi-phase case? And so one way I could kind of indicate that was creating the slice plane and then plotting or computing the density on that slice plane. So for this time step, at time equals 10 seconds, I saw that the average density on that slice plane was 302 kilograms per meter cubed, indicating that, okay, we do have some fluid flow going through that slice plane where it's increasing the overall average of density. Lastly, we can also compute the mass flow rate of a surface or, again, a derived entity. So just the basic inputs to this are the surface of interest, and then we also need to provide a density value in order to compute that MDOT. So the user can select just a constant value, or if they have derived variables available in that data set, they can actually use the field value of density to look up what that is and compute the mass flow rate. So just last few slides here. I just wanted to kind of get a handle on what size data sets we could read and how long it takes. So I ran through 4 models. Here are 2 of the smaller ones. We had all of these are ultrafluid X cases. For the small fan, there was about 90 million voxels. It takes on the order of a minute or less than a minute to load, and takes about 3.7 gigs. For a similar model, but yeah, it has slightly more voxels and more parts. Again, we have our read times down tremendously fast, and then the memory usage is still acceptable here. It's 32 gigabytes for that drive air case. If we go to sort of the larger side of our model testing, we have 2 models here that I'm showing. One is this ultrafluid X test case for CAA. It's 526 million voxels. It read in about 4 minutes and used 125 gigabytes. And similarly, sort of the high-end model was a SUV. This was a benchmark case that was 550 million voxels. It again took just about 4 minutes to read. And in this case, I pretty much saturated the disk on one of the Oracle machines, or saturated the memory at 134 gigabytes. So I was at least happy to see that these read in and had a pretty quick read time. The memory usage is a bit high here. So actually for 0.3, we're looking to target reducing that memory usage by kind of throwing away a small part of the data set that we do believe is acceptable to do. So we're looking to improve that memory usage for very large ultrafluid X cases in the 0.3 release. The end of my slides. Thanks everyone for listening.